We will take a quick look at whether increasing model resolution actually improves or reduces model biases. When we improve resolution, some of the first things that happen is that the orographies like the Western Ghats, the Himalayas, are going to be better represented. So you would hope that the orographic processes, orographic precipitation related heating, the waves and so on are going to be captured better and improve the dynamic representation of the monsoon, the extremes and so on. Also the increased resolution is going to capture additional processes of atmospheric and oceanic circulations that are coupled. So if you have very coarse resolution, then you have propagation speed differences in the waves and associated impacts, local and remote, and so on and so forth. So quickly, the same paper that we looked at before by 2017, so I cited it somewhere, I hope I didn't. Okay, it's this paper. Okay, it's this one here from Climate Dynamics in 2017. And so you can see here we are again looking at the annual cycle and the monsoon dynamics, which is defined as the tropospheric temperature gradient and the vertical shear. So U shear, so it's positive here and negative here. So looking again with the data, so TRMM and Aphrodite, you can see that the data themselves are not that close to each other. So Aphrodite is down here at about 7 millimeter per day in maximum amplitude, whereas TRMM is well above 8, so it's almost 9 millimeter per day. That difference in heating itself is going to be pretty significant, especially if you integrate over these monsoon months, right? This is critical as well. And remember, TRMM is satellite data, and Aphrodite merges lots of data, including in situ data, and this is another data set, the authors WM, and that's closer to TRMM, but depends on how they produced their data product. So looking here at the low resolution model and the high resolution model, so the red line is the low resolution model, which is shifted in its peak compared to observations, which are in peak here, even though amplitudes are different, and the onset and withdrawal are different in the low resolution model compared to observations, whereas improving resolution or increasing resolution has definitely improved the transition here in the beginning of the season, even though the peak is not improving, but the amplitude of rainfall has changed. It has become closer to Aphrodite here compared to the low resolution run, and the withdrawal maybe it's getting closer to the observations, but it's still quite biased compared to observations, but then the two observations are slightly different from each other as well. So this is something that implies that the increased resolution does improve certain things. Does it mean improving resolutions further is going to further improve the model results? And do these improvements come with increased active break accuracy as well, increased meso propagation as well, and so on? Those are detailed questions that have to be looked at in addition to just these results, but I just wanted to give you a sense that improved resolutions are considered, and the evaluation of changes in dynamics and thermodynamics are looked at. And this is looking at temperature, and you can see here the temperature bias is greatly reduced, impressively reduced, I would say, by improving resolution. So that's definitely good news. Depending on the parameterization of convection, you have to see if reduced temperature bias is related to this improved rainfall features as well, in terms of the onset and the withdrawal and so on and so forth. Looking here at again the resolution impact on dynamics in terms of meridional temperature gradient in the troposphere and the vertical shear, you can see that there is a change. So the red line here is low resolution, and the blue line is the green line is the line with green dots is the high resolution, and you can see that it does get better compared to Aphrodite here, or TRIM, one of them, observational data. So you can say that overall there is an improvement in the circulation in terms of the meridional temperature gradient and the vertical shear, both of which are related to circulation and diabatic heating and so on and so forth. So just to look a little bit further, monsoon onset here, TRIM observations, low resolution. You can see that the observations are way off here compared to TRIM. The high resolution model definitely improves that compared to TRIM in this corner, and maybe in this peninsular India as well, and parts of these central, northeast, and northeast as well. So yes, resolution, at least in the model considered, makes a difference. But then when you look at the low pressure systems or monsoon depressions and compare it to NSAP-NCAR reanalysis, which we use here as observations, which itself has a little bit of a bias, so one has to be careful, and it's not clear. So low resolution model seems to be doing more of this clustering origin here and termination over there, but the high resolution model seems to have introduced a bias of more of them propagating or originating away from the cluster here, and the number and the propagation clustering is also different. So this is the challenge. If the mean is improved, that doesn't mean that subseasonal variability or synoptic scale low pressure systems and depressions are improved. Again, one has to look for consistency in the dynamics. Let's run through a few papers which are listed here in the paper by Dipti Singh and colleagues. Key findings from studies of projections of subseasonal extremes and their related processes. Different scenarios are considered. 4.5 is our representative concentration pathway. 4.5 is a medium emission pathway with resulting radiative forcing, anthropogenic forcing of 4.5 watts per meter squared by 2100, whereas 8.5 is the extreme emission scenario of business as usual, and different models are looked at here. So let's just look at some of the processes to try to understand the range of conclusions that people come to. Highest rates of increase in 5-day accumulated precipitation over South Asia relative to other monsoon regions. Warming, so the scaling of 7 to 10% per Kelvin. Although the differences between 1.5 and 2 degrees C levels of warming are spatially variable. So they have compared the warming rates and the sensitivities to warming in terms of accumulated precipitation changes, and conclude that the highest rates occur over South Asia relative to other regions, and the scaling is 7 to 10%, and it changes by the degree of warming. This paper concludes robust increases in exceedance of historical maxima in near, mid and late 21st century, particularly over southern India, which is peninsular India. So they are looking at different metric and looking at near-term, mid and late century projections. It does matter because there is some evidence that the near-term projections are more related to model uncertainties, whereas longer-term, late 21st century projections are more related to scenario uncertainties. I will say that, but you can look up the details. Increase in intraseasonal variability, intensification of active and break spells, higher frequency of short duration active spells, and short and extended breaks, amplification in magnitude of low frequency mode. So multiple processes are concluded from this paper that we just looked at, Sharmila paper. Looked at a subset of CMIP5 models listed here. I won't say which models are which, but you can look that up as well. So this is Japanese, Chinese, German, and Norwegian, and so on. Okay. So multiple changes are noted in terms of the subseasonal extremes, and their related processes are not mentioned, just diagnostics phenologies are mentioned. Sabir Ali looked at the German model with one scenario to conclude that increase in meso variance over the Bay of Bengal, western coastal and equatorial Indian Ocean, and to a lesser extent over central India, decrease in speed of northward propagation but increased amplitude. So warming is argued to reduce the propagation speed but increase their amplitude. How does that relate to the rest of the low frequency dynamics in circulation changes, thermodynamic changes, precipitation efficiencies, and so on also have to be looked at. But this relates directly to the subseasonal extremes on land in this model at least. Okay. Menon et al. Enhanced daily variability of all India rainfall. This kind of may be consistent with the increased spatial variability of extremes and changes in return periods versus subseasonal extremes and so on. So one can say intrinsic time scale is the intraseasonal variability, but diurnal cycle is always there because sun goes up, sun goes down. Diurnal heating is a very dominant mode of forcing, so diurnal variability in rainfall makes a big difference to see how its variability changes. Turner and Slingo with one model and doubled CO2 experiment rather than a particular scenario conclude fewer wet days, intensification of heavy rainfall, intensification of active and break spells without changes in duration or frequency. So this is somewhat different than the Dipti's conclusions about historic, and other papers have done the same. Historic changes in break and active spells. Active spells are supposed to have become shorter term, around 6 days, and they have become more intense, but break spells have become more frequent but less intense because of increased humidity, whereas this one says intensification of active and break spells are both changing, but their duration and frequency doesn't change in a double CO2 experiment. This paper looked at older set of models, CMIP3, to conclude that increased duration, strengthening and expansion of break spells. Increased duration, strengthening and expansion of break spells. So it didn't say much about active spells, but CMIP5 models are different, at least in terms of consistent changes in resolution, improved resolutions in general for all models. Also improved processes, maybe more carbon cycle, CO2 feedback. Some of them had better vegetation, soil moisture, and lots of other processes, including CMIP5 submodels even had land ice and so on and so forth. So you have to see where this change comes from CMIP3 to CMIP5. Regional high resolution models, so these are kind of dynamically downscaling models, so they are constrained by global models. One has to keep that in mind because the forcing global model giving boundary conditions may make a difference as well. So Sandeep et al. Reduced synoptic activity, so you can think of them as low pressure systems at 3 to 10 days. Weakening and poleward LPS genesis, so the low pressure systems were generated more in the northern Bay of Bengal. More genesis over land, increase in 95th percentile extremes in the Indo-Gangetic plains and southern India, and decrease in central India. So there is a shift in intensity and distribution of 95th percentile extremes. Dynamics are not mentioned, but one has to look at that as well. Statistical downscaling that I mentioned before for the RCP 8.5 scenario. Enhanced spatial variability, increase in average annual maxima over central India, and fewer extremes in parts of northeast. So these are using historic data to do statistical downscaling of the future projections. There are methodologies involved which you have to look up, but they are a good way to think of in terms of using historical biases and uncertainties to constrain the future, which is a good way to provide better constrained what-if scenarios for the future. Okay, LMDZ is a stretched grid model from France, which is a global model but stretches the grid locally to produce downscaling. Increase in frequency of heavy rainfall events greater than 100 millimeter per day over central India. So we should remember that most models say in the future the land warming is faster heat capacity effect compared to the ocean. Aerosol effects are uncertain, but nonetheless most of them project increased mean monsoon rainfall, but this one also says increase in frequency of heavy rainfall events in the future over central India. Okay, RED-CM is a popular regional climate model. Projects increased frequency of break spells, suppression of the dominant oscillatory mode of variability. Okay, look up the details. Another study by so the 2015 paper we kept looking at for biases is by Ashfaq et al. Also from 2017. RED-CM here concludes increase in number of monsoon depressions with speeds greater than 15 to 20 meter per second. Okay, doesn't talk about the change in frequency or let's say genesis regions, but says the number with higher wind speeds which are getting into the tropical cyclone range is going to increase. And finally, I think it's Krishna Kumar et al. Which used the PRECISE model constrained by HAD-CM3 and HAD atmospheric model. So this is coupled model and atmospheric model to constrain the regional downscaling. Argued that increase in 1 to 5 day precipitation maxima over western, coastal and central Indian Ocean are projected in their configuration. What do you do with this? Basically, you have to remember that we are still dealing with uncertainties in representation of precipitation processes. In general, higher uncertainties even in the mean precipitation in most of these models, and then the uncertainties in extremes. So each model is looked at for its scaling in terms of radiation balance and relation to Clausius-Clapeyron. So per each Kelvin warming, how much precipitation changes and how much the extremes change, and then you look at changes in precipitation efficiency, saturation, vapor pressure and dynamics in terms of vertical velocities. And then you come up with these conclusions for the future. So one has to take all that into account while using the projections for any sorts of decisions on water resource management of agriculture, adaptation in terms of reducing the impacts of flash floods, droughts and so on and so forth. Okay, but you get a sense that models are providing you a range of scenarios which have to be used together in some ways to draw conclusions for policies and decisions.